So we're going to talk about merge sort. The way merge sort works, the strategy is this. We're going to split the list in half. Exactly in half. We're off by one if it's not a number. And then we are going to recursively sort each half. Now, when we do that, we won't be done yet, right? Because if we sort the left half and we sort the right half, we're not done. We have to merge them back together again. Does that make sense? Two arrays, both sorted. I need one big array that's sorted. I'm just going to merge those two back together again. Okay. So, and now thinking about it recursively, I'm going to do that once when the size of the array is 12. And so I can think of it as, okay, I'm dividing it into two lists of 6. I'm sorting each list and then I'm merging them back together again. Done, right? But how am I sorting the list of 6? Well, I'm dividing it into 2, sorting each half, merging them back together again to get a list of 6. And then I could keep going like that, right? So just kind of a big picture, trying to get you sort of a little bit of a big picture of how this is going to work. So here's my array. These are the same numbers that we were sorting last time. First step is just divide it, take the first half of the list and sort that. Take the last half of the list and sort that. Right. So this is just going to be like, so I guess maybe if there's a hard thing to conceptualize about that, it's how do you call the same function, but only send it half of the array, right? The way we're going to do that is whenever we call merge sort, we are always going to send it a low and a high that tells us which part of the array to sort. Okay. All right. So I split it in half. I get these two lists. I split those two lists in half. Whoa. That's not what I was expecting. Now I have all of these. I'm going to split those in half. My Windows skills are weak. Sorry, I'm just going to go for it here. All right, so we split the list of 3 into 2. So one of the lists is going to have 1 item. The other list is going to have 2 items. And then to sort these, really in real life, probably at this point, you'd write the code to just compare them and put them in the right order, right? But we're going to just follow it all the way through. Split this list up into 2, 55, 92. Same here, same here. Oops. Same here. Okay, so don't look at the combining back together again part yet, but you understand how we're splitting these all up, right? So what's the base case going to be in merge sort? When do you stop recursively calling itself?
Yes, one element.
When there's one element in the array, right? And well, when the portion of the array that you're being told to sort has a size of 1, right? In fact, I think it might even be, we might even, let me just check. Yeah, that sounds right. Having size issues again. You zoom out. Command, there we go. Okay, right. So I'm going to keep recursing as long as start is less than end. So when they become equal, I'm done. Okay. So another way of saying that is that if you call merge sort and start and end are equal, Merge sort does nothing. It's just done. Okay, so now what happens is, as I mentioned at the beginning, we've got, just take an example, this list here as an example. We have divided this into two halves. Now we need to merge those two lists back together again to make one list that is sorted. So there you have that. Does that make sense? Now, if I was drawing this all out as we go, I'd be drawing this down the page anyway. So I think you're getting the same experience.
Yeah.
Anybody want to try to ask a question? So basically, every time you get to a list of size 1, you're going, so let's say we've got a list of size 2. Okay, so what we do is we divide it in half, we sort the left half. It's only got one item in it, so it's sorted. We sort the right half, it's only got one item in it, so it's sorted. And then we merge those back together again. Okay. So now what we have to do is we've got these oddballs sitting out here because we had a list of size 1. We've got to merge this with the 4360 to get it back so that it's a list of 3 and it's sorted, right? So we're going back to this list here, except now it's going to be sorted. Well, it already was in that case, but that was just coincidental. So taking a look at this one, we started off with a list 67, 90, 38. We split it in half. We split it in half again. We merged those two lists back together to make a sorted list. And now we're going to merge the 67 back with those to make what used to be this 67, 90, 38 is now sorted.
So when do the comparisons happen? They happen, I mean, in the single elements, they happen when you merge those, and then if the oddballs happens after that, it looks like.
So the comparisons are going to happen in the process of merging the two lists back together again.
Okay.
Okay. Which we'll take a look at. Okay, so now we have, our 4 lists with 3 each. We're going to merge this list here with this list here to get a sorted list. And we're going to merge this list here with this list here to get a sorted list of size 6. Okay, so now just to make sure you're tracking with me on this, this list here of 6 is the same list we started with, except now it's sorted, right? So looking at it from the top level, what we've done is we took this list, we divided it into 2 halves. We sorted each half. That's where we are now at the second to last line. And now we're going to merge those 2 sorted lists together to make one sorted list. Okay. That's the procedure. If I gave you a list of 12 numbers, could you copy this template? Okay, probably just look at the picture and not even understand what's going on. You could just kind of follow the same patterns, right? I will just mention as an aside, somebody, I don't know if you guys have noticed, have read this yet or not, but someone in the discussion pointed out that the code that I provide does it slightly differently than what I'm doing it here. The code I provided, this person pointed out, actually puts 2 items in the left list and 1 item in the right list. So if there's an odd number of items, it puts more items on the left side and fewer items on the right side. So it's backwards, but doesn't really matter, I don't think. I could change it in the code, I suppose. I'm not going to recreate this picture.
In the middle,
Yeah.
where these 2 are split up,
Yeah.
how does this 82 node just sit in limbo until this step all the way down here?
So how does the 82 node just wait until this list is done before it merges back together again? So let's think about the recursion. When I have this list here, the 82, 55, 92, I call merge sort with the left list, which is 82. I call merge sort with the right list, which is 55, 92. When both of those calls to merge sort are done, then I merge them back together again, right? But part of the process of calling merge sort on the 5592 is that it's going to call itself recursively to put that list in the right order and then come back.
Yeah, so 82 would have returned true a few steps before it gets merged back in with the 55 and 92.
Yes.
So when the recursion have ended a few steps sooner.
So, I mean, this actually, if you look at this picture, these are exactly the function calls as they're happening. So I'm going to call merge sort with 82. And it's just gonna come back done because 82 is already sorted, right? And then I'm gonna call merge sort with the 5592, and it's gonna do whatever it does. It's not gonna come back until those two are sorted, which is down here.
Mhm.
So now I'm gonna merge. I called merge sort with the 82. I called merge sort with the 5592. Now I know those are both sorted. Now I'm gonna merge them back together again. So it's just another way of saying that is that the larger list took more recursion to get the same job done. Anyway, that's actually pretty, in pretty good shape if you can visualize that part of the recursion. I mean, I think a lot of students who are computer science majors, they're able to reproduce this, they're able to at least understand the code, but they may not have that level of being able to sort of picture what's going on with the recursion. Okay, so the point so far with merge sort is that you could follow through this process again. I just the downside to using a picture that I already created is I told you the answer, the big O answer. I don't know if you saw it. You did. Okay. Pretend you didn't see it. Just kidding. So let's analyze it. Let's talk about the big O. Okay. Each step here, as I am dividing the lists up, so down to this point, requires constant time. Probably just like 2 or 3 operations, something like that, right? I'm just calculating the midpoint, calling merge sort on the left half, calling merge sort on the right half. The calling merge sort takes more time, but just the process of splitting it in half and making the calls is just 3 or 4 steps. Okay, so that part of the process, that part of the algorithm is not going to be significant. We can pretty much just ignore that. Let's look at the merging back together part. The first thing I want to ask is each of these steps. So there's 1, 2, 3, 4 passes through the array where I am merging things back together again. Each one of those steps is going to take how long?
What was one for the previous step?
Basically just n, right? So let's look just for a second. Let's look specifically at the very last step, right? I've got a list with 6. I've got a list with 6. I can merge those back together again into a list of 12 that is sorted, just looking at each item in the list once or twice. So it's going to be a function of n, not n squared or 2 to the n or anything like that, just function of n. Might be 2n, might be 2n plus 17, but it's going to be linear. The same thing is going to happen going from the third to last line down to the second to last line. Or I guess I could say the second to last merging. I'm going to do the same thing. It's just that I'm doing it in 2 halves, right? I'm merging these 2 lists together to make this 6. This list of size 6, and then I'm merging these 2 over here on the right to make this list of size 6. Same thing is happening. I'm looking at each of these numbers in the array once or twice to get that job done. So bottom line so far, each of those steps of merging takes n. So the only question left is how many times am I going to have to merge those lists back together again? So if I have a list of size 2, how many times do I have to merge them back together again? 1. I really want to draw this out. Give me a second here. Oh, and I have to change the share. let's just do the whole screen. Okay, not quite sure how this is gonna go with trying to show everything on the screen at the same time, but let's just do our little algebraic table thing, okay? This is n is the number of items. We'll call it f of n for now, for lack of a better way of saying it, is how many times we are going to have to merge back together again. So if there are 2 items in my list, I'm going to have to merge back together 1 time. If there are 4 items in my list, how many times am I going to have to merge back together again? 2. Oh, that's not a 2. If there are 8 items in my list, how many times am I going to have to merge back together again?
4, 3.
I'm going to start with 8 separate things. After merging 1 time, I'm going to have 4 lists of size 2. After merging a second time, I'm going to have 2 lists of size 4. After merging a third time, I'm going to have 1 list of size 8. Right? So you can see what's happening here, right? If I have a list of size 16, how many times am I going to have to merge it back together again?
4.
4. Whoops. And so on. So what do we see? What kind of function are we seeing here? It's a logarithmic, right? And if you're not sure why it's logarithmic, I would just say it like this. To get from, if I was asking it the other way around, it would be exponential, right? The first column is 2 to the right column, right? And so as soon as I see that, even if I don't understand what a log is, I know it's the inverse of exponential. So I know that what I have here is a logarithmic function. Okay, so back to our diagram. We know that each time we merge, it's n. We know that how many times are we going to merge? Log of n. So the total process is going to take. So if I do something, if something that I do takes 7 steps, and I have to do that 8 times, how many steps is that?
8 times 7.
Right, 8 times 7. You multiply them together. So this is I'm something that I'm doing is taking n steps, and I'm doing it log n times. So the amount of time it's going to take is n times log n. So that's what we have here. And that's basically, that's an efficient sorting algorithm. You're not going to get better than that in terms of the big O. For a general purpose sorting algorithm. Is that a big win or a little win? It's a pretty big, it's a very big win. So for example, let me back up just a little bit. Is there more about merge sort, or about the analysis that we need to talk about, or is that we're pretty good with why it's big O in log n? Okay. So let's just play with the numbers a little bit, okay? So the other 3 sorts we did: selection sort, bubble sort, insertion sort. They were all n squared, right? Now we're talking about a sort that is n log n. So I want to know if I have, I'm going to have to make this a lot wider. If I have 1 million items, which is not actually all that many, right? I mean, nowadays we're talking about data that we're storing that's, you know, unimaginably huge, right? But just start with 1 million. How many steps is it going to take if I have a big O n squared sort? 1 million times 1 million, right? So 1 trillion. But Okay, and we can start maybe doing some calculations about how long that's gonna take. How many steps is it gonna take if I have an log in algorithm? Depends on what log of a million is, right? So here's what, so I know this is tricky, but this is actually, I don't know. I'll just tell you. So this is actually a fairly good thing to have memorized if you're going to be a computer science major. So 2 to the 10 is about 1,000, right? A million is 1,000 times 1,000. 2 to the 10 times 2 to the 10. 2 to the 20, right? So 1,000 is about 2 to the 10. 2 to the 20 is about a million. 2 to the 30 is about a billion. 2 to the 40 is about a trillion. So just like that. So log of a million is, we just said, is 20, right? So the number of steps that's going to take, instead of being 1 trillion, we skipped over a billion, right? Is going to be 20 million. That's a pretty big win, right? Let's say that we have a computer that does 1 million operations per second. That's actually pretty slow, probably, right? But just let's go with that, just to see. So if we have a computer that does 1 million operations per second, how long is the big O n squared going to take? 1 million seconds. How long is that? Isn't it like millions of years or not millions, but so let's do it real quick. Okay, I'm just gonna, I got my calculator out here. Divide by 60 to get how many minutes it's gonna take. Divide by 60 to get how many hours. Divide by 24 to get how many days. So 11.5 days. Okay, and that's with 1 million items, right? Admittedly, it's with kind of a slow computer, but imagine if you got 1 billion items.
Like 31 years.
If you've got 1 billion items. So yeah, 31 years is probably too long, right? But let's say, what did we call this? 15 days? 11 days, 11.5. That's where I got the 5. Okay, and the n log n sort 20 million operations, 20 seconds, right? Pretty big win, right? Yeah. Okay. So just to give you an idea of, this is why big O is important, right? This is why we can ignore the details. We don't care if it's 2n or if it's 3n, that doesn't matter. What matters is which category of functions it falls into. In other words, what the big O is, right? That's what makes the important differences. Not to say other efficiency issues aren't going to matter, especially if you're in a context where things have to happen pretty instantly, right? But that's just sort of hammering around on the edges in terms of getting something to be really efficient. Okay. Let's look at code. Here's my merge sort. So there's the merge sort function. That's it. Not bad for what seems like a fairly complicated algorithm, right? Does that make sense? So the base case is when start gets to be equal to end, right? Because in that case, the function just ends. The recursive case is, as long as start is less than end, call merge sort with the left half, call merge sort with the right half, merge them together. Okay. The actual merging process is a little trickier. It's not really complicated, but it's just a little tedious. Okay. So there's the code for that. Basically, what I have to do is I have to create a new array. And then I just go through the 2 arrays and with pointers at the 2 arrays, and I say, okay, If the left one is less than the right one, put the left one into the new array and move the left pointer up one. If the right one is less than the left one, put the right one into the new array and move it up one. Keep going until one of them gets to the end of its array. And then whatever's left in the other array goes at the end. That makes sense?
Yeah.
Okay. Let me maybe just do that in a teeny tiny bit more detail. Whoop, where did my, oh, I know where it went. It went. So let's talk about merging this list on the second to last line, these two lists on the second to last line, and making the one list on the last line. So I'm basically going to have a pointer at the 38 and a pointer at the 15. 15's less, so I put the 15 in the new array, and then I bump the pointer up, not technically a pointer, an index, but I'm going to call it a pointer, to the 35. So now I've got a 35 over here and a 38 over here. So I'm going to grab the 35 because it's lower, put it in the array, and then bump it up to the 43. Now I'm looking at the 43 and the 38. The 38's less, so I'm going to put the 38 in the array, and I'm going to bump that left pointer up to the 55. Now I'm comparing 55 and 43. 43 is less, so I put the 43 in there, and I bump the 43 up to the 53. You get the idea, right? Okay. So basically, we're just going down, and we're only looking at each item once or twice. Okay. I think I'm done talking about merge sort. Do I know I kind of waved my hands quite a bit on the code. It's not that bad if you really want to get into it. It looks a little bit scary, right?
Yeah.
But all I'm doing is I'm saying, okay, count is going to be the pointer at the new list that I created. Left is going to be the pointer into the left list that I'm merging. Right is going to be the pointer into the right list that I'm merging. And then as long as I haven't reached the end of either array, if the thing on the left is smaller, put it in the new array and bump it up one. If the thing on the right is smaller, put it in the new array and bump that pointer up one. Okay. Then when I'm done with that, the situation is that I'm at the end of one of the two arrays. So I'm going to, these two while loops, only one of them even executes, and it just take the rest of whatever's left over in the list that I did not get to the end of and put them in the new array. Then I have to copy that new array back into the original array and deallocate that temporary array that I made. Okay. So this one's a little different in that it is not in place. That makes sense? In place means I just moved numbers around in the array. I didn't have to create a new array, right? This one, you have to create a new array and then copy it back. All right, I think I'm done talking about merge sort. Yes.
So it says pointer to the left half of the list.
Right.
Is that a pointer or just a regular?
It's just an int.
Just-
It's an int. I'm using the word pointer because visually, that's what I'm seeing. I'm pointing a finger at one and I'm pointing a finger at the other. Or if I was drawing on a whiteboard, I'd probably draw an arrow to it. But it's actually just an index. Good question.